This only holds if there is no air drag, no friction of any kind. That is very unrealistic if we are near Earth, but when we are farther away from Earth, as we were with the KC-135, which was flying at an altitude of about 30,000 feet, that of course is a little bit more realistic. And therefore the example that I have picked to throw up an object is the one whereby the KC-135 at an altitude somewhere around 25 or 30,000 feet comes in at a speed of 425 miles per hour, turns the engines off, and then for the remaining, whatever it was, about 30 seconds, everyone, including the airplane, has no weight. So that's the case that I now want to work out quantitatively with you. In the case of the KC-35, we'll take an angle for alpha of 45 degrees, and we'll take V0, which was about 425 miles per hour. You may remember that from that lecture. 425 miles per hour translate into about 189 meters per second. And so that means that the velocity V0y and V0x are both the same because of the 45-degree angle. And that is, of course, the 189 divided by the square root of 2, and that is about 133 meters per second. Both are positive. Keep that in mind, because this is what I call the increasing value for y. And this is the increasing value of x. They're both positive values. Signs do matter. So this is a given now. And now comes the first question that I could ask you on an exam. When is the plane at its highest point of its trajectory? And how high is it above the point where it started when it turned the engines off, when it went into free fall? So when is it here, and what is this distance? Well, when is it there? That's when the velocity in the y direction becomes 0. It is positive, gets smaller and smaller because of the gravitational acceleration, comes to a halt and becomes 0. So I ask this equation, when are you 0? This is the one I pick, and so I say 0 equals plus 133 minus 10 times t. You may think that the gravitational acceleration at an altitude of 30,000 feet could be substantially less than the canonical number of 10. It is a little less, because you're a little bit further away from the Earth, but it's only 0.3% less. And so we'll just accept the 10. It's easy to work with. And so when is it at the highest point? That is when t equals 13.3 seconds. So that's about how long it takes to get there. When I gave the lecture last time, I said it's about 15 seconds, because I made the numbers, I rounded them off. It's about 30.3 seconds. And what is this distance h now? Now I have to go to this equation. I say h equals 0, because I'm going to define the point where the plane starts its trajectory. I call that y0, 0. I'm free to do that. H equals 0 plus 133, that is the speed, times 13.3 seconds, minus 1/2 times g, that is 5, times 13.3 squared. That is what h must be. And that turns out to be about 885 meters. I think I told you last time it's about 900. It's close enough. So we know now how long it takes to reach P, and we know what the vertical distance is. And the whole trip back to this starting point, if we call this sort of the starting point, starting altitude, this whole trip will take twice the amount of time. To get back to this point, when the engines are restarted, is about 26.5, 27 seconds. How far has the plane traveled then in horizontal direction? Well, now I go back to this equation. So now I say, aha, x then, when it is back at this point, must be x0, which I conveniently choose 0, plus 133 meters per second, which is the velocity in the x direction, which never changes. When the plane is here, that velocity in the x direction is the same 133 meters per second as it was here, which, by the way, is about 300 miles per hour. That never changes if there is no air drag or air friction of any kind. So we get plus 133 times the time, and the whole trip takes 26.6 seconds, and that, if you convert that to kilometers, is about 3.5 kilometers. Now you could ask yourself the question, what is the velocity of that plane when it is at that point S? And now, you may want to abandon now this one-dimensional idea of x and y. You may say, well, look, this is a parabola, it's completely symmetric. If the plane comes up here with 425 miles per hour at an angle of 45 degrees, then obviously it comes down here at an angle of 45 degrees, and the speed must again be 425 miles per hour. And you would score 100%, of course, it's clear. I want you to appreciate, however, that I could continue to think of this as two one-dimensional motions, and I can therefore calculate what the velocity in the x direction is at S, and what the velocity in the y direction is at S. So what is the velocity in the x direction at point S? I go to equation, the second equation there. That is V0x. That is plus 133 meters per second. What is the velocity in the y direction? I have to go to this equation now. V0y minus gt. So I get plus 133 minus 10 times the 26.6 seconds to reach that point S. And what do I find? Minus 133 meters per second. The velocity in the y direction started off plus 133, but now it is minus 133. You see, this is sign sensitive. This is wonderful. That's the great thing about treating it that way. So you now know that it comes in with a velocity of 133 in the x direction, positive 133 in the minus y direction. And so what is the net? The sum of the two vectors. That, of course, is this vector. And no surprise, this angle is 45 degrees. And this one is the square root of 2 times 133. And that, of course, gives you back your 189 meters per second. 189, this is a 9 meters per second. And that is 425 miles per hour. I'm not recommending that you would do this. Of course, it is perfectly reasonable to immediately come to that conclusion because of the symmetry of the parabola.